This is Polars, one of the fastest DataFrame libraries in the world. If you've never touched a DataFrame library, simply think of it as a tool for filtering and summarizing tables with billions of rows. The kind of work Excel does, just much bigger. It's the modern challenger to Pandas, and in published benchmarks, it runs 30 times faster. Part of that is because it's written in Rust. But the biggest performance gains don't come from the kind of safe Rust most of us write every day. The biggest speedups come from a part of Rust most developers never touch: Unsafe Rust. So in this video, I'll explain the 5 ways Polars uses Unsafe Rust for blazingly fast optimizations, and how you can apply the same techniques to your own projects. The first unsafe optimization is Unchecked Indexing, and it is by far the most common use of Unsafe Rust in Polars. Here's a function that adds up values at a specific set of row positions. The same operation Polars runs internally every time you group rows and sum a column. This line looks like it does not cause any performance issues, but it does. Every iteration compares I against the length of values to make sure it is in bounds. This is a safety check that Rust inserts automatically, and it is a good thing to have in general. But in this case, the developer knows that every I is valid, so the check is unnecessary. If you run that over 100 million rows, then you will have done 100 million check bounds. That's a lot of repeated work. So here we update our loop with getUnchecked. The developer is guaranteeing that every I is in bounds, and the compiler trusts that promise. You get the same total and none of the repeated work. And this is the pattern behind roughly 1,000 uses of getUnchecked across Polars. Make the developer responsible for proving the index is valid, and you save a lot of work. If you have your own project with a hot loop that is doing a large amount of repeated check bounds, you can apply this same pattern to get a big speedup. The second unsafe optimization is building a buffer without initializing it with zeros first. This is a common pattern in Polars aggregation kernels. This vector initializes every slot with 0. That could be 100 million zeros. But then immediately you overwrite every one of those zeros with another computation. Polars avoids that wasted work with a few small changes. First, Polars reserves the memory without initializing it with a value, using vec with capacity. The allocation happens, but not a single value is written. Then it gets access to the reserved memory. Spare capacity mute returns a slice of maybe uninit, telling the compiler the memory is allocated but not initialized yet. The loop now writes each computed value straight into the slice, so every slot gets written exactly once, and none of them were ever zeroed first. The last step is to use an unsafe block to set the length of the vector manually. SetLen tells the vector it now holds n real values, and you as the developer are guaranteeing every slot was actually initialized. If even one slot were still uninitialized, reading it would be undefined behavior. The third unsafe optimization shows up the moment Polars starts to use parallelism. This is real Polars code, which is a wrapper around a raw pointer mute t. Sync pointer allows Polars to create one vector and then give access to that vector by sharing the pointer across multiple threads. This saves a lot of memory and redundant copies, because normally each worker in a thread pool would have to create its own vector, and then they would all be merged together at the end. But typical safe Rust will not let you give a raw pointer to another thread. Raw pointers are deliberately not send and not sync. Being send means a value is safe to move between threads, and being sync means a value can safely be accessed by multiple threads. So Polars overrides that decision by manually implementing the send and sync traits on sync pointer. Implementing these traits is unsafe because the compiler can't verify the type is thread safe. It has to trust your promise. This override now allows raw pointers to be sent and shared across threads. You are promising that the pointer is safe to send and share, and the compiler trusts you not to introduce data races. While sharing a pointer across threads is a very common pattern in Polars, it is also a very common source of bugs in Unsafe Rust. For example, if 2 threads accidentally write to the same memory location at the same time, the result is undefined behavior. If you are going to use Unsafe Rust to share a pointer across threads in your own project, you have to be very careful to avoid these data races. Unsafe optimization number 4 is explicitly declaring deterministic iterator lengths. Normally, an iterator's length is just a hint. Rust does not know exactly how many items an iterator will produce, so it keeps growing the output vector as new items arrive. TrustedLen is a marker trait promising that the iterator's length is exact. This allows pollers to read the length once, upfront, and allocate the exact amount of vector capacity needed. No rechecking, no extra allocations. TrustedLen is an unsafe trait because if an implementer gives the wrong iterator length, then that may lead to undefined behavior, and the compiler cannot stop it. But if you're in a similar situation of always knowing the length of an iterator, you can use an unsafe trait like TrustedLen to skip repeated checks and get a big speedup. Unsafe optimization number 5 allows us to reinterpret bytes from one type to another without copying data. In our case, we're going to convert a column we have in Rust to its C-compatible counterpart in 2 key steps. This is simplified code, but shows what's really happening under the hood when pollers talks to Pandas or DuckDB. First, it exports the column to Rust's arrow array type. That is a Rust struct that wraps the raw bytes of a column and gives them a Rust type. Then, it uses transmute to reinterpret the Rust arrow array as a C-compatible FFI arrow array type. This is a C struct that wraps the exact same raw bytes, now labeled with a C type instead of a Rust one. A critical point is that transmute validates nothing on its own. It does not check alignment for you, and it does not check that the bit pattern is valid either. If the layout is wrong, you get silent corruption. This is why transmute must be wrapped in an unsafe block. This is exactly why it lives at small boundaries. It's a very precise tool that has to be used deliberately in a small fraction of the code. You'd reach for this in your own code anytime two types share an identical memory layout and you need to hand that data across a boundary, FFI, a network, a file format, without paying the cost of copying it byte by byte. These are the 5 unsafe optimizations that Pollers uses to be one of the fastest DataFrame libraries in the world. And yet, as a consumer of Pollers, you never have to write unsafe yourself because the library is carefully designed to keep all that complexity inside. And if you're interested in learning how to write production Rust, check out our Rust Live Accelerator. It's our tailored mentorship program where we help developers go beyond YouTube videos, build production-grade Rust software, and land their first Rust job. You can join the waitlist for our next cohort by heading over to letsgetrusty.com/join or by clicking the link in the pinned comment below. When you join the waitlist, we'll also send you our Rust developer roadmap as a small gift. So tap the link, join the waitlist, and I'll talk to you very soon.